I'll say recall solving trigonometric equations. Steps building up. All right, so one, solve Trig function equals a number. Stop me if you have questions, by the way, online or in class, and I'll try and answer them. What do we do to solve a trig function equal a number? Here's what you can do is put u, or whatever your favorite letter is, equal the angle. I think I said theta, didn't I? Theta equal the angle. And solve on the unit circle. Solve for theta unit circle. Right. This is a real, let's leave it like that. And then put in terms of the original variable and apply any restriction. X, say, because I'm liable to say find x only between 0 and 2 pi. I only want the direction, not all the rotations. So applying any restriction 0 to 0 less than or equal to x less than 2 pi, if given. Right? Now the second thing was I might have a linear equation. I won't go through all the details of that, but solve a times a trig function plus b equals 0. This is called a linear equation and a trig function because it's like ax plus b equals 0, a linear equation in one variable x, except I replaced x with a trig function. Now what do? You just write equivalently that by subtracting b, dividing by a, write trig function equals minus b over a, which is now a number. Right? Oh, it's trig function equals a number. Apply method 1. So you just put it into that form, trig function equals a number. Finally, and this one got to be pretty hard for a while, right? To solve a quadratic equation in a trig function. A times trig function squared plus b times the trig function plus c equals 0. How do we solve that one? Just let your favorite letter, such as u, equal the trig function to get a quadratic equation. AU squared plus BU plus C equals 0, right? And then we said from that equation, we know in algebra we can always solve it, right? Factoring is often a fast way. So we might want to factor it. However, sometimes the factors are difficult to guess, and sometimes it doesn't factor at all. In that case, if you can't figure out how to factor it, you apply the quadratic formula, which you have to memorize for the test because it'll be on there. I'll list it again, right? U equals minus b plus or minus square root b squared minus 4ac over 2a. You can also complete the square, which is equivalent to applying the quadratic. This takes longer. We didn't do that. Easier to use the quadratic formula. And then you do that to get a linear equation step two, or just u equals from the quadratic formula, in which case you go to method one. So this one reduces to this one or this one, depending on whether you use factoring or the quadratic formula. All right, so that's what we had, and now we should do a additional example. There's a lot of subtleties left out in here, right? One trouble was that sometimes it says exact solutions, and it's not a special angle, and it's very difficult, and you have to put it in terms of inverse trig functions. So when we get down to method one here, and we actually have to solve it for exact case, we want to leave the answer in terms of inverse trig functions. Sometimes I'll say round, in which case you want to put it in terms of decimal values for the inverse trig functions. But you always wind up going down to solve on the unit circle in any case. Does that look familiar, I hope? Let's look at a couple more examples here. Well, this is still a review example, but it's sort of a new example, right? A new review example. Suppose I said this, solve by any method. And I gave you this one. Cosine squared x, and let's say exactly. For 0 less than or equal to x less than 2 pi. And I get cosine squared x plus 3 cosine x plus minus 1 equals 0. How about that one? What would I do with that? Thing to do is just think of those steps. Which method do I use? This is a square of a trig function, first power, and just a constant. This tells me it's a quadratic equation and a trig function, right? So I go to method 3. This is so, and I just let u equal cosine x and observe when it becomes a quadratic equation. All right, I put u equal cosine x, and this gives u squared plus 3u minus 1 equals 0. Now, how do I solve the quadratic equation? I can try factoring. Pulling out all the stops here on this one. If I factor a quadratic equation, quadratic polynomial here, it's always blank u plus blank u plus blank. And there are numbers that go in the blank, but sometimes they are complex. They have square root of minus 1 in them, and so you can't figure them, and we can't use them in this class. But this always does factor. It's just not necessarily in terms of real numbers. And what happens if you think about it from the quadratic formula is if b squared minus 4ac is negative, you'll get a square root of a negative in the quadratic formula, and there will be no solution. So if this is negative, we don't have anything to do. There are no real solutions, just imaginary ones. Imaginary numbers. But in this case, b squared minus 4ac, if I call this a is 1, b is 3, and c is minus 1, make sure you put c on the left and put 0 on the right by itself, and the quadratic formula won't work. B squared minus 4ac is 3 squared minus 4 times 1 times 1 is 5. That's positive, so what do I know when the discriminant b squared minus 4ac is positive? I know I'll get two solutions. If I factor, if I use the quadratic formula, it doesn't matter, they give me the same solutions. When b squared minus 4ac is positive, you get two solutions. Recall from algebra, b squared minus 4ac equals 0, you get one real solution. Plus and minus in the quadratic formula give you the same result. And if b squared minus 4ac is greater than 0, less than 0, then you got no real solutions. They're all just have square root of negative 1 in them. All right? So we've got here two solutions in this case. I wonder what goes in the blanks. Well, in order to get one u squared, I need one here and one here. I could put minus 1 and minus 1, but then you factor a minus 1 out and cancel them outside, so there's no point. So these are ones in the blanks. And now I just have to figure out what goes in here and here. And I recall that the product, right, because the product of these has to be 1. Product of these blanks has to be this one, has to be minus 1. So this is product equals minus 1, the constant term. And these, the product of those two always has to be the coefficient of u squared. So this product has to be 1. Now that means I have to put 1 in one of these and minus 1 in the other, or something that's just too hard to guess. So the only thing you can guess, the only integers you can put in. Let's see, I get u squared minus u plus u is nothing. Minus 1. Oh, that just gives me u squared minus 1. That's not this. So what's wrong? Nothing's really wrong. It's just that what goes in the blanks is difficult. The only possible integers that go in the blank numbers and nothing after the decimal point don't work. So factoring fails because what goes in the blanks actually has some nasty square roots in it. So it's too hard, we'll say. There are actually numbers that go in the blanks. We know from the discriminant, there's two real number solutions. This is a hard algebra lecture here. Quadratic formula. In the quadratic formula, if you get a square root of a negative number, there's no solutions. That's when b squared minus 4ac is negative. When you get a square root of 0, the plus and minus give the same one solution. But when they're positive, when b squared minus 4ac, the so-called discriminant, is positive, then there's plus and a minus in the quadratic formula. There's two solutions. And that's this case, which means there's things that go in the blanks, but sometimes you can't guess them. It's too hard. So I'm going to, when factoring fails, go to the quadratic formula. Some of these say use any method, and that's the idea. You can use factoring if it's easy, but here it's not easy. So I'll try the quadratic formula. And it says u equals minus b is minus 3 plus or minus square root b squared 4 times a times c all over 2a. And I got minus 3 plus or minus square root, let's see, 9 plus 4 is 13 all over 2. How about that? Wow. No wonder I couldn't have guessed what goes in the blanks. You know how this factors? If I did factor it, guess what goes in the blanks? This is how every quadratic polynomial like this, we call it, every left-hand side factors. You take the lead coefficient, put it out here, and then u minus blank, u minus blank, and whatever formula, quadratic formula says, that's what goes in the blanks if you put minuses here. So you put the lead coefficient here, and then u minus blank, u minus blank. And what had to go in here was minus 3 plus square root 13 over. Minus 3 minus square root 13 over. Wonder we couldn't guess, it was too hard, right? So when these nasty square roots go in here, you just have to go to the quadratic formula. You never guess by factoring, right? These are the solutions, though. Now, u, however, is cosine x. So I just have to solve cosine x equals that. Camera over. And there's two solutions, right? So now, I'm down to cosine x equals minus 3 plus square root 13 over 2, or cosine x equals -3 minus square root of 13 are the possible solutions there. And now what do I do? Trig function equals a number. I go to method 1. That's the idea. When you get a quadratic equation at trig function, that's the hardest one. I'll give you one of those on the test at least. Apply either factoring or the quadratic formula to get either trig function equals a number or a linear trig equation, like we did last time, and you just go to the previous method. It just takes you to previous method, nothing more than that. Now, this one, what do I know? Square root of 13 is bigger than 3, right? The square root of 9 is 13. So this whole thing is less than -3. I have something that's less than -6 on the top over 2. The whole right side is less than -3. So what are the solutions here? This has no solution. I need cosine x equal a number less than -3. It's impossible, right? So this one has no solutions because you can't make cosine a number bigger than 1 or less than -1. So that takes care of that side. That was easy. But now over here, this is between 3 and 4, right? Square root of 13. Square root of 9 is 3, so it's bigger than 3. Square root of 16 is 4, so this is less than 4. If I take a number between, if I take -3 and add a number between 3 and 4, I will get a result and divide by 2. I will get a result between plus and -1, so this one has a solution, right? So this whole thing here is between -1 and 1. Think about it for a second. So it has a solution. I just have to solve this on the unit circle. Cosine x equals -3 plus square root 13 over 2. Then you have to think about it. This is between 3 and 4, right? So this is actually positive, right? -3 plus a number bigger than 3 is positive, and then divided by 2 is still positive. And so this is cosine x equals a number. How do I solve cosine x equals a number on the unit circle? I say the cosine is the x coordinate on the unit circle. Maybe we call this x hat or something. So cosine is the x coordinate, x hat around the unit circle. And whatever number this is, maybe I don't know. I can run in the calculator, but I don't need it. I just know it's positive, so it's over here somewhere. And this can be the line of all coordinates. X hat equals -3 plus square root 13 over 2. Right? And I observe that there's exactly 2 points on the unit circle where the cosine of the angle is equal to this x coordinate. Here, there's exactly 2 terminal rays where cosine is equal to this number, whatever it is. So what are all solutions to this problem? Well, I go around and figure those angles, right? Here's one, and here's another. What is this angle right here? This is about as hard a problem as you'll get all semester. It doesn't really get harder than this. What angle is that? Somebody can tell me. I know it. You just got to think for a second. This angle satisfies cosine x equals this number. Then we know one solution always to this is x equals the inverse cosine of this number, right? That's always one solution when this number is between plus and -1. So there's one solution. Which is it? Is it this one? Is it this one? Where is it? Well, it's always between, right? Arc cosine always gives you a number between 0 and pi. So it's not this one. It's between 0 and pi. It's this angle. This angle, one solution, is x equals arc cosine minus 3 plus square root of 13 over 2. That being the case, what's this other angle here that goes all the way around but short? Tough one, huh? Well, look, by symmetry, this one and this one are the same, right? They're the same. They hit the unit circle the same distance over, drop to the same point. So this distance here, the cosine is the same for them. This angle here must be 2 pi back up the arc cosine. Minus 3 plus square root of 13 over 2. That's it. There are exactly two solutions between 0 and 2 pi. The one just barely. X equals arc cosine minus 3 plus root 13 over 2, or x equals 2 pi less that arc cosine. Those are the exact answers. If I ask for exact answers, you just leave it in terms of arc cosine. Then whoever wants to evaluate that can get as many digits as they need by running to a machine that does. Okay. Now we get down to the last part that says now we have to apply any restrictions. I don't have to apply any restrictions on here because the angle was just x and I got all the answers between 0 and 2 pi. If the angle had been 2x or 3x or a half x or something, I would have to check. I would have to add plus 2k pi. So this would be all answers, right? Arbitrary k rotations. Then I'd have to restrict it to 0 to 2 pi, but because it was just cosine x, not cosine of a multiple of x, we don't have to, that'll just reduce it to the 2 we found. So these are all solutions between 0 and 2 pi. We don't have to put these unless we want, unless we're not going to apply a restriction. Okay. So there it is, a very difficult problem with pretty much all the tricks in there, except at the very end, we didn't have to apply any restriction. We didn't have to put plus 2k pi and then throw out the x's because we started with angle x, a multiple of x. So that was the last method we did. We said sometimes we have pretty nasty answers, but we can still write them exactly in terms of arc cosine. Might on the test say give a decimal answer. In that case, you just have to evaluate this on your calculator and give the decimal version. There's nothing more to it than that. Now the last step, step 4, and this will finish the whole chapter, and then you'll be experts at this stuff. Well, this is as hard as it gets, really. If more than one trig function is present. Sometimes that happens. Right, so far, we've just been dealing with just cosine or just tangent, just one trig function at a time. Here's what you do. And by the way, these techniques are not for every single problem. These are the common techniques everybody uses. There are other things besides this fourth method. But for us, all the problems will be ones you can solve like this. Either you can eliminate the extra trig functions. Let's say reduce to one trig by trig identity. So if you see too many trig functions, use Pythagorean identity or something like that to reduce it. Reduce to one trig function by an identity. That works on a lot of the problems. And the other thing that happens on just a few of these is you can put the equation equals 0, put 0 on one side, and factor with just one trig function in each factor. I'll give an example of this and then it'll make sense. Right now, it probably doesn't make sense. But if you do that, then you can reduce it to method 1 or 2. So if you reduce it to one trig function by any method, or if you put 0 on one side and factor with one trig function each factor, now a previous method applies. 1, 2, or 3. Okay. So that's the last method. It's 1, 2, 3, 4. And here's a few problems now coming off the homework this time. Suppose I gave you this one. This is 7a. Sine squared x minus cosine squared x minus sine x equals 0. And again, solve on 0 to 2 pi. And remember this notation, solve on 0 to 2 pi means that x is between 0 and 2 pi. The square bracket at the left means include equals, but the round bracket on the right means don't include equals. So that's what this means, right? Now, how can I do one of this is more than one trig function, right? It has sine and it has cosine. Anybody see anything how to reduce this to a single trig function by an identity, or we already have 0 on one side, factor it with just one trig function each factor. Factor means right as a product, right? Factors are things that are multiplied together. When I say terms are things that are added together. Factors are things that multiply.
Could we use the Pythagorean?
Yeah, there you go. Whenever you see a square of a trig function, think Pythagorean identity. If I replace cosine, that's exactly right. Cosine squared with 1 minus sine squared by the Pythagorean identity, sine squared plus cosine squared equals 1. That will get rid of the cosine and we'll just have sine in here. So that's what I can do here. I'll rewrite it equivalently like this. It's equivalent because cosine squared is always 1 minus sine squared by the Pythagorean identity, solve for cosine squared. Now I've got it, because when I group like terms, I've got sine squared minus a minus sine squared is 2 sine squared minus sine x minus 1 equals 0. A quadratic equation in one trig function. Go to method 3, the one we were just doing. Right. And I'm gonna better wait just a second, probably writing online. Method 3 says put or substitute u equal the trig function you see, sine x, to get a quadratic equation, right? 2u squared minus u minus 1. Now we can try either factoring or the quadratic formula. And based on our last example, we might be tempted to say, well, why not just go to the quadratic formula? It always works, after all. And sometimes factoring doesn't, right? However, on this one, I think, if you just think for a second, it's blank u plus blank, blank u plus blank. This one is easier to factor than use the quadratic formula, right? You can use either one. The quadratic formula always works. If you want to just use that on a test, that's fine. But here I look at it and I say, I can see exactly how to factor that. In order to get 2 here, the product of these has to be 2. So I'll put 2 in one and 1 in the other. 2 times 2, and so I take this times this, I'll get the 2u squared. Now what goes in here, their product has to be minus 1. So I put minus 1 here and 1 here, or minus 1 here and 1 here, and those are all the ones I can guess. The other ones, if there's anything else in there, I'll have to get by the quadratic formula. But this works often. Let's see what I get if I put it this way. 2u squared plus 2u minus u is plus u. Oh, not minus u. But look, if I put plus 1 there and minus 1 here, when I FOIL, this is 2u squared minus 2u, this outside, plus u inside, minus 1. Sure enough, this is minus u. That worked. So this is the way it factors, and I can look at it and guess it right off. I don't have to go to the quadratic formula. So this time factoring is better, but both work. All right, I'll clean this up just a little bit. You don't have to write another step. It's 2u plus 1 times u minus 1 equals 0. Same thing. Okay, so far? Well, here I have two trig functions, but I use an identity, the Pythagorean identity, to reduce it to 1. Notice it's a quadratic equation in sine x. So I'll let u equal sine x and solve this one by factoring. Now remember the zero product property says either this is equal to 0, which makes u, well, let's 2u plus 1 equals 0, or this one equals 0. Product is 0, u minus 1 equals 0. Well, this is 2 sine x plus 1 equals 0. And this one is u minus sine x minus 1 equals 0. Oh, it's a linear equation of trig function. So now I'll go to method 2. So I apply method 4 because it has two trig functions. Reduce it to a quadratic equation of trig function. Then I apply method 3 to reduce it to two linear equations. I said method 1. Now apply method 2 for linear equations of the trig function. I think I'm okay. Okay. Method 2 now says, you just write each of these. 2 sine x minus 1 equals 0. You subtract 1 and divide by 2 and get sine x equals minus a half. Or here you just add 1 to each side and get sine x equals 1. Trig function equal a number. Go back to method 1. You know, it's like the house that Jack built. It gets step by step, it gets there. All right, now you solve each of these units circle. That was method 1. All right. Reduce it to quadratic equation, reduce it to linear equation, reduce it to trig function equal number, solve on the unit circle. 4 steps on this one. So I can get solutions from either unit circle. Sine x equals minus a half. Well, this is the y coordinate. If I call it x hat, y hat over here, distinguished from this x. But if the y coordinate on the unit circle is minus a half, it's this line right here. Y equals minus a half. There are exactly 2 points on the unit circle where the y coordinate is minus a half. Consequently, exactly 2 terminal rays, this one and this one, will make the sine of x equal negative a half. Over here, I want sine x equal 1. Well, again, that's the y coordinate. I'll call it y hat equal 1. And that's this horizontal line here, right? Y equals 1. It intersects in only one place to make sine x equal 1. So there's only one terminal ray possible, this one. Sometimes that happens, it's just tangent. Right? So this time, got on this circle, I've got just one solution between 0. So my solutions, let's see, I got to figure this one out by dropping perpendiculars. This one, I notice it goes down to y equals minus a half, so the side length is 1/2. So unit circle, so this is 1. That makes, oh, this is a 30, 60, 90 triangle. This one by the Pythagorean theorem will have to be square root of 3/2. This angle right here will have to be minus pi over 6, minus because it's clockwise. Well, if I want solutions between 0 and 2 pi, then I shouldn't get that one. I should go around this way to this one and around this way to this one and say, really, what I want is these two angles, not to go negative. I'm solving between 0 and 2 pi, right? I'll say this one right here is, let's see, again, if this is pi over 6 here, then this will have to be pi over 6 here too. 1/2 on this side, 1 here, it's 30, 60, 90 triangle. So I've got pi plus pi over 6. This time I don't have to leave it inverse in terms of inverse trig functions because I got lucky. It's a special triangle. I get the exact angle 7 pi over 6 without needing any inverse trig functions. Similarly over here, it's 2 pi back up pi over 6. How to subtract these things, you put them over a common denominator. 2 pi is 12 pi over 6. Subtract pi over 6. Once they have a common denominator, you subtract their numerators. 12 pi minus pi is 11 pi. All goes over 6. So there's two angles between 0 and 2 pi. X equals 7 pi over 6. X equals 11 pi over 6 from the first circle. Now over here, there's exactly one angle between 0 and 2 pi. Since this goes straight through the top here, that angle is pi over 2 evidently. That's a good solution. This one has 3 solutions. How about that? Now these are the solutions in 0 to 2 pi. You can add 2k pi to each of these. But since we said before, we're going to restrict to 0 to 2 pi, that's the final answer. That one look okay? That's the kind I'd like to get in the test. I think it's not too hard of numbers. And it illustrates a lot of the important points. It gives all 4 methods. You know, it is true, as I said, is you don't ever have to factor on these. You can always just go to the quadratic formula. But I really need to present that in class because lots of people in practice use factoring. And because actually if you get higher degree equations than second, factoring is sometimes necessary. So even though I say in the test you can solve all these equations quadratic in a trig function by the quadratic formula, do please learn the other methods so you'll be able to in later classes do higher degree equations. And so that when somebody else does factoring, you'll know what they're doing. All right, now I want to look at number 8. It's the last problem on here. This one, it says, solve around, use a calculator to find the value in the interval 0 to 2 pi around the 2 decimal places. So solve around 2 places after the decimal point. And when they put that on the homework, and when I put that on the test, that normally means that we're not going to get special triangles like we did in this one. Special triangle, you don't want to write decimal places. You want to write in terms of pi, right? This is warning us ahead of time. We're not going to get a special triangle. We'll just have to use inverse trig functions for these. These are kind of hard. And again, tangent is the hardest function. Let's look at 8a. Say tangent squared x plus 3 tangent x minus 3. Actually, let's write it this way. I'm going to put equal. You see this one on the test. What's the first thing you should do? Yeah, put the 3 over here, the minus 3, so it's equal to 0. And recognize it's a quadratic equation in tangent. So I'll go to method 3 here. It is only one trig function, so we're safe there. Method 3 we let u equal tangent x and observe that this gives us u squared plus 3u minus 3 equals 0. So I didn't need method 4 on this one. It only had one trig function, right? Now, maybe I can factor it. Those are nice small numbers. The last factoring doesn't work. Are you advanced enough? You want to see how you can tell ahead of time if factoring is going to work? Yes, no. Factoring works. It leaves whole numbers you can guess if b squared minus 4ac is a perfect square, a square of a whole number. So if I get 1, 4, 9, 16, 25, 36 a square, then I'll be able to guess what goes in the blank. So if you want, you can figure b squared minus 4ac ahead of time. 3 squared minus 4 times 1 times minus 3. 3 squared plus 9 plus 12 is 21. That's not a square. Therefore, there's no sense trying to guess what goes in the blanks. It's going to have nasty square roots or imaginary numbers. And now this is 21. It's greater than 0. I'm going to get two solutions, right? See why this is so important in algebra? Everybody says, why do we need to know this? But I know because b squared minus 4ac is positive, I'll get two solutions. But because it's not a square, I know there's no point in factoring. I'm gonna have a square root of 21 in there is what's gonna happen. So instead of trying to factor, I'm gonna go to the quadratic formula directly. Do that whenever b squared minus 4ac is a positive number, not a square. I just say right off, or just do this right off if you want on the test. Minus b plus or minus square root b squared minus 4 times a times c all over 2a is minus 3 plus or minus square root 21. See, it wasn't a waste of time calculating that. I needed it in the quadratic formula anyway, right? All over 2. There it is. If you factor, that's what would go in the blanks, right? This factors actually, you don't have to know this because it's algebra. 1 times u minus blank, and what goes in the blanks are these numbers, minus 3 plus square root 21. Or 2 minus 3 minus square root 21. Who would ever have guessed those, right? So you just do the quadratic formula and save yourself some time, right? So method 3 says put u equal tangent x, I should have put, and apply the quadratic formula. Now, u, however, was tangent x. So I've got trig function equals a number. I go to method 1, all the way back to method 1. Because it's trig function equals a number. I'll put tangent x equals the first case, minus 3 plus square root 21 over 2, or tangent x going to be minus 3 minus square root 21 over 2. Now, last time we got cosine x equals a number bigger than 1 or less than minus 1. I said, aha, no solutions. We don't have to work so hard. Could that be the case here? No, tangent x can be anything. So we're going to have to solve both these in the unit circle, right? Tangent looks like this. But if I've got tangent x equals a number, there'll always be a solution. Solutions if you count rotations here. So both of these will have a solution. It's just if you see sine or cosine, they can only be between plus and minus 1. Secant and cosecant, since they're reciprocals, have to be greater than or equal to 1 or less than or equal to minus 1. We don't have too many of those on the homework. That starts to get technical and difficult. But so tangent can have a solution for any number, any real number. Let's just solve both of these on the unit circle since we're right. Trig function equals a number, even if it's a messy number. Once again, I'll give an x hat, y hat axis. with the idea, I don't want to get this x mixed up with then this x is the angle. I'd rather put tangent theta than I see. But the idea is that tangent theta is y over x. Oh, great, I can't do that, right? If it was sine, I put y equals it. I put a horizontal line, but cosine, I put a vertical line, but tangent is y over x. What do I do with this one? Well, I say to myself, I know one solution is, what is one solution to this? X equals what is one solution to that? Tangent x equals the number one solution is always inverse tangent, right? Or arc tangent. Inverse tangent minus 3 plus square root 21 over 2. That will be one solution. Where is it? Well, with a lot of finagling, right? Square root 21 is bigger than square root 16, so this is bigger number than 4. That makes minus 3 plus the number bigger than 4 positive, and that divided by 2 is still positive. So tangent has to be a positive number. That means the angle is in quadrant 1 or quadrant 3, and I don't know how to measure it approximately, but if I put it in quadrant 1 or 3, it's good enough. And remember, tangent equal a number always has two solutions, and they're directly opposite each other. Two solutions like this, one in quadrant 1 and one in quadrant 3. That's what's going to happen. And whatever they are, one of them is going to be arctangent. Which one is it? Is it the angle here? Or is it the angle here? I told you these are hard. Which one is the arctangent? I know it has to be quadrant 1 or 3 because right, this is a positive number. That's tangent is positive in these two quadrants. What values can arctangent be? For its always between minus pi over 2 and pi over 2. Does that sound familiar? So it has to be this one. This one is the arctangent. That makes this one what? Directly opposite, so it's arctangent plus pi, a straight angle. Arctangent x plus arctangent of that number minus 3 plus square root 21 over 2 add pi. Those are the solutions. And I think this says between 0 and 2 pi again, right? Yeah, I should have put it on the instructions. X in the interval 0 to 2 pi. So this is all I'm going to have to do is find those two angles. There they are. I just have to run these in my calculator. Arctangent minus 3 plus square root 21 over 2. The same plus pi. Those are the solutions in the first circle. Now this one has another unit circle. This is negative, right? It's a negative minus another number is clearly negative. Divided by 2 is negative. So this one's going to be in quadrant. The angle x has to be in quadrants 2 or 4 in order to have a negative value. So I don't know exactly where that is, but it doesn't matter. I'll just put it in the quadrant here. And I get directly opposite angles again. There'll be one in each spot. Now, one of those is the arctangent. Which is it? Arctangent is always the angle between. So it's this one. This one is the arctangent of this number minus 3 minus square root 21 all over 2. Now, this is a homework problem, so write this down. Then when you do it yourself, you can figure it out. That's this one. That's not a solution to our equation. Why not? I told you it's complicated, huh? Yeah, it's negative. Yeah. So it's got to be between 0 and 2 pi. So I don't want this angle. I want this angle. What is that angle? 2 pi plus this angle. Why don't I subtract this angle? already negative, right? So I take 2 pi plus this negative angle gives me this one. So this angle that I want is 2 pi plus the arctangent of -3 minus square root 21. That's what will be this angle. 2 pi plus a negative angle, this one, gets me right there. So that's one solution to the second circle. And then what's the other one? That's this one. Now I can take pi and back up this amount. Again, it's adding this negative angle. So this one is actually pi plus arctangent minus 3 minus root 21 over. There it is. 4 solutions. Put them down here, I guess. Pi plus arctangent minus 3 minus root 21 over 2. 2 pi plus arctangent minus 3 minus square root 21 over 2. 4 solutions to this. But those are the exact answers. Alas, on this problem, I said not exact answers, decimal, right? So now you got to be very careful with your calculator, right? To calculate this one, I just push the following keys. Second tangent, recall this is on right now. Second tangent gives me the inverse tangent, right? Because inverse tangent is up above in the colored key. Push the colored key in and enables the instruction above. Automatically puts in a parenthesis on some calculators, 2 parentheses. I need a negative number. I push the little minus key, not to subtract. Down at the bottom, there's a little minus key with parentheses. Minus 3 plus, to get square root on most of these calculators, I need second x squared because the square root sign is up here. Square root, it inserts another parenthesis or 2. Square root, now I got to put in 21. These are not easy to put in by calculator. Now I probably have to close my parenthesis. If it has 2 parentheses, then you go out of here instead of closing the parenthesis. And you put minus 3 plus square root 21. And now I realize to my horror, I have to divide the whole thing by 2. So what do I need to do? If I put divide by 2 now, it'll just divide this one by 2, right? Because it'll do the division before the addition. What I have to do is say that, well, there are implied parentheses. This long bar makes implied parentheses here. All right? That's what the long bar is for. It says there's implied parentheses here. So what we have to do is go back here and put in a parenthesis here and a parenthesis here. This one you always need in order to include the whole top and divide the whole thing by 2. So divided by 2. This is the beautiful thing, however, about these programmable big screen calculators is that we'll show you exactly what you typed in and you can check it, right? All right, so divided by 2, and now I may have to close the parentheses for the arctangent. And let's see, did I close the square root here? X squared, square root 21. Yeah, may have to close the parentheses for the square root, and may have to close the parentheses for the arctangent. On this one, you do. This is an old count. Let's try that, but you look at it and see if it looks like that. And on your homework, when you try it, the answer is in the back. Let's see if I can get the right answer. Arctangent, -3. Oops, I forgot my parenthesis already. Left parenthesis, -3 plus square root second x squared. This is why you have to practice. This is long if you don't practice it. Square root 21, close parenthesis. Close parenthesis for the numerator. Divided by 2, close parenthesis. And I strongly advise you on these things. On the TI 84 and 83, it automatically closes all parentheses. That makes you feel secure because it calculates it. I strongly advise you on this one to close all your parentheses because what happens is if you forget one in here, it will close them all for you and give you a number. But so if you left out a left parenthesis, it will give you the wrong number. If you put in all your closed parentheses, this will force it to tell you whether you put them in a sensible way or not. So when I put it in here, then I'll see if this makes sense. If it gives me error, then I try again. This comes out to be 0.6694, blah, blah, blah. We'll round that off and call that 0.67, since it said the 2 decimal places. So that's the first answer there. What about the second answer? I gotta move this over again, I guess. You know you're in trouble when the problem takes up the whole board, right? What about the second answer? It's supposed to be that plus pi. Here's how you get the second answer easily without typing in all those digits and fat fingering it. For the second answer, this is the first one. But second answer, you can get back whatever was just on the screen by pushing second, the little minus sign, because it says ANS above, and it brings back the last number on the screen. I'll take answer plus, to get pi, the pi can come out exactly on here. I push second, this calculator caret. This has the answer that just came up on the screen plus pi. And then I'll get lots and lots of digits. Let's try that. Second answer plus second pi. Now I push equals and I get, and it should look 3.14 bigger than this one. You can hand this by hand, I suppose. And I'll get 3, but if I ask for more digits, it's not so easy, right? 3.8109, blah, blah, blah. So this is approximately 3.81 to 2 decimal places, right? The instructions don't say round to 2 significant digits. They say round to 2 decimal places, 2 places right at the decimal point, right? And if this number is 5 or bigger, I round it up to the next digit. If it's not, then I leave it as is. So the second answer is 3.81. Let's see if that looks like the answer in the back after all. Tracing this and I can't cover it. Hopefully it's right. On the test, I think you should check your answers. That's, this much detail, it's easy to mess something up. 7.5. I think this is right, but let's double check. That's number 8. Yeah, 0.67 and 3.81. So these are exactly what's on the back. This is how it was obtained. When you do problem 8A on the homework. These are very long problems, so get going on these now. Try and bring in questions next time. Any questions on that so far? Rather than be real detailed around it, let's just say the next one, arctangent minus 3 minus square root 21 over 2. It's just like calculating this one, just with a minus here. And then what you get is on the back, third answer, when you take pi plus this number, as it comes out to be, all these have been checked. Oh, it doesn't give them. We never checked these, I wonder. That's interesting. This actually does have an answer. Arctangent equals any number always has a solution, right? Because of picturization, right? The tangent looks like this. If you want tangent equal to a number, you know, if you say I want it equal to this number, there's always a solution. If I want to equal this number, there's always a solution. So tangent equals any number always has a solution, unlike sine and cosine. Well, I'm going to have to do these by calculator then. Third answer, just so you can check your answers at home. This actually has 4 answers, and we better put them on. Arctangent. I had one of the fancier calculators, the TI-89 or the Inspire. You can actually go back and edit your old answers and change the plus to minus. That's one of the advantages of those. I don't have that calculator here today. Arctangent parentheses minus 3 minus square root 21 close parentheses. divided by 2, close parentheses. And then I'm gonna have to add pi to that. Well, let's just do that for now. That would give me minus 1.384, this arctangent. So on the calculators, you get minus 1.4, blah, blah, blah. Then if you add pi to that, plus second pi, you get the first angle is 1.75. So the third answer would, checking how many, oh, it's 1.75758. So it rounds up to 1.76, right? That's the next digit is 5 or greater. And then the fourth answer, you can just add pi to that because it's 2 pi plus the angle. So I add pi to that plus pi. I put plus pi and 4.8997, blah, blah, blah. Rounds to 4.90, right? This next digit is 5 or greater. I have to round this up to 4.90. Put down the 0 because if you don't, it's assumed you rounded to tenths, not the nearest hundredth. This indicates that last digit is significant. I'm going to write those down. I would forget to do this anyway, but it'd be good to try. 3.81. Oh, that's not 1.76. 4.90. Okay. We're good on that one then. If you can do that one, you can do just about anything. I did promise you we'd do one more of these though that we need to. Yeah, let's see. Yeah, let me run the screen back to the other side. In this last one, there's just a whole lot of trickiness going on. Get started this early, and I think you'll do well on this test because it is only one chapter. You just have to work these, they take a long time. And then after this chapter, everything goes back is a little easier. So this is the last really, really difficult material this semester. Let's try this one. Let's see it now. Yeah, 7D. Suppose I had cosine 2x minus cosine x equals 0. Well, 0's on the right-hand side. That's a good start. And again, let's solve and 0 to 2 pi. See what solutions we come up with. Right? That's the first thing I should do. In some sense, I don't have just one trig function. Why? This angle is 2x and this angle is x, right? I can't just say this is a quadratic equation or a linear equation in cosine. This one's cosine 2x and this is cosine x. So this falls under the category of having more than one trig function, even though they're both cosine. This is cosine of one angle, this is cosine. So I'm going to say I have to go to method 4. Because cosine 2x, if you use the double angle formula, is really cosine squared x minus sine squared x, right, by the double angle identity. So apply an identity, rewrite that in terms of cosine x. Now I've got it. It's actually in more than one trig function. It has a sine and a cosine in it. Once I use the double angle identity. So this is tricky, right? I'm trying to show you how you can do these last few problems. Now what do I do with that? Remember, if I've got more than one trig function, I get rid of it with an identity, right? I'll replace sine squared with 1 minus cosine squared. Put this in parentheses People who leave out their parentheses, this is what they do in the next step. They say, oh, this is cosine squared x minus 1 minus cosine x squared x minus cosine x equals 0, and that's wrong. What did I do wrong? Wrong in there? I'm subtracting sine squared x. I have to subtract the whole thing. Put this in parentheses, so you put minus 1 minus minus is plus cosine squared. This should have been plus. Subtract the whole thing when you make the substitution. Put that in parentheses. Now I see this is 2 cosine squared x minus cosine x. I'm going to arrange it in the standard order. Minus 1 equals 0. I put it in the order, so the cosine squared and then the cosine and then quadratic equation in one trig function. Now I can go finally to method 3, right? So I start with more than one trig function by the double angle identity. Reduces to a quadratic equation, one trig function, cosine x. So I let u equal cosine x, and it will now become a quadratic equation. 2u squared minus u minus 1 equals. Simple numbers, that looks like maybe I can factor it. And sure enough, I can. Again, if factoring becomes difficult, you just go to the quadratic formula. That always works. But for practice for later classes and so forth, it's nice to try factoring now. So I'll say this is equivalent to blank u plus blank u plus blank. I sound like I'm trying to call somebody a bad name. You feel like after you're done too many of these, they're pretty hard. All right, and what goes in those blanks to make 2u squared minus u minus 1? All right, well, I need a 2 and a 1 because the product of these has to be 2. And I need these two to have product minus 1. Again, if I put minus 1 here and plus 1 here, it'll be 2u squared minus 2u plus u is the minus u minus 1. Sure enough, when I FOIL that to check, it comes out to be the left-hand side too. Put minus 1 here and plus 1 here, I'll get it wrong, and then I'll know to switch it. Now, if the product is 0, then either 2u plus 1 equals 0, that factor is 0, or the second factor, u minus 1 is 0. Either this is 0 or this is 0. Linear equations, method 2, right? So the factoring reduces it to 2 linear equations. To solve 2u plus 1 equals 0, I subtract 1 and divide by 2 and get u equals minus a half. This looks very much like our last problem, right? Or in this one, I get u equals 1, right? Alas, this time it's cosine equals a number, these numbers. So it's going to be a little different, right? So method U2 reduces this to, should put it as trig functions, I don't know. 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. Let's put it that way. And then say you solve, these are linear equations in cosine x, so it's equivalently subtract 1 divided by 2, cosine x equals minus a half. Or this one, add 1 to each side and get cosine x equals 1. Method 2 says I just subtract 1 divided by 2, I add 1 over there, and I get this. Trig function equal a number, it's method 1. All right, so I'm marching back from 4, 3, 2, 1. Almost to 0, right? Then we're done. Method 1, when we have trig function equal a number, we solve it on the unit circle. Now these numbers, 1 and minus a half, are between plus and minus 1, so these will have solutions. If you get something bigger than 1 or less than negative 1, you say, oh, all done. Solution in that case. So I'll solve each on the unit circle and combine all their solutions, right? We say take the union of the solutions. Now cosine x is the x coordinate, so I'll call this x hat on the unit circle, is equal to minus a half, so it's right here, right? So I want all x coordinates on the unit circle, x hat, y hat, to minus a half. There's exactly 2 points in the unit circle that have x coordinate minus a half. So there's only two terminal rays, this one here that can make cosine x equal minus a half. You figure those angles on these, we can figure exactly, right? If I go half a unit left of origin on this side of the triangle is 1/2. This is 1 because it's unit circle. I recognize a 30, 60, 90 triangle. All right. So this is a 60-degree angle here, pi over 3. By symmetry, this is also pi over 3. Right? It's also got a side 1/2. So I observed from this first case, there are solutions. Now let's see. Pi back up pi over 3 is 2 pi over 3. Pi go forward pi over 3 is 4 pi over 3. If you work at it a little. That's the two on this one between 0 and 2 pi, right? How about this one? Cosine x equals 1. Well, again, cosine is the x coordinate of the circle that I call x hat. So here's all coordinates x equals 1 on the unit circle. There's only one point on the unit circle that has x equal to 1. That's this one, theta equals 0. So the last solution here is 0. Easier for a change. Right. So this actually has exactly 3 solutions. You can find them exactly. I didn't ask you to round it. On the test, I'm going to ask you, find these exactly, round these to so many decimal places if it's not special triangle. So sometimes you get special triangles, you write it exactly. Sometimes you don't, you got to round it. All done. We can do some more of these if you want. I haven't finished them all even. These are long problems, but that gives you the whole flavor of the section. Maybe I should do one more here actually when I think about it. Let's try one more because last one. This one is 7G, and this one another trick also. Suppose I have minus 3 sine t. Let's call it theta. It uses t here. Let's use theta. Equals 15 cosine theta sine theta. They solve this on the unit circle. On the interval 0 to 2 pi. How about that? How would I go about that one? Use your recipe book, right? More than one trig function, I need method 4, right? So method 4. How do I get rid of the trig function? Well, this is going to be method 4b. First thing I want to do is, here's a temptation, all right? Don't do this, all right? What if I just say, wait a minute, there's a sine x, I can divide through it, right? This is minus 3 equals 15 cosine theta. What's wrong with that? I just lost some solutions, all right? You can divide an equation on each side by any non-zero number, but if I have this, like x squared equals x, I can't divide both sides by x and say, oh, this is equivalently x equals 1 by dividing both sides by x. What have I done? I divide both sides by x, I assumed x wasn't 0. Now this had 2 solutions, 0 and 1. This one I lost one of them. I only have 1 left. So you can divide each side by a non-zero number, but you can't just, if you divide by a variable, you have to take into account maybe that variable was 0 and do that separately. So instead of writing this and losing some solutions, right, because sine theta equals 0 will give us solutions. Instead, get 0 on one side and factor. Let's put 0 equals 15 cosine theta sine theta plus 3 sine theta. All right? So I'll put 0 on one side. And I'm gonna factor, but easier, if these both have a common factor of 3, I can divide through by 3. 3 is a non-zero number. I can divide both sides by 3 and it won't change the solution set. I just gotta be careful about dividing by sine theta or cosine theta. They could be 0. If I divide by 3, this becomes 0 equals 5 cosine theta sine theta plus sine theta. There it is. So now this equation is entirely equivalent to this one because I just subtracted. You can subtract both sides, any number. It can be 0, doesn't matter. And then I divided by 3 is a non-zero number. So this one is equivalent to this one by subtraction. This is equivalent to this one by dividing both sides by a non-zero number. Now, how do I solve this equation when it has more than one trig function? Instead, we're going to use method 4b. The last method here is to factor this thing, getting one trig function in each factor. So it's tricky. 0 equals, and I notice both these have a sign in it, so I'll factor out the sign as 5 cosine theta plus 1. There it is. All I did was factor. This one is equivalent to this one by factoring. How do you see how to do it? Once it's factored, product equals 0. Either this factor equals 0 or this factor equals 0. 0 product property. If product is 0, at least one of the factors is 0. So this before and the other one when we factored quadratic equation. So this is equivalent to sine being 0 or 5 cosine theta plus 1 equals 0. Right? Equivalent to those two statements. Either this factor is 0 or this factor is 0 or both. So let's solve. I'm going to move backwards, I think. I can solve each of those on the unit circle. This is trig function equals a number, method 1. This is a linear thing. I can go to method 2. Say by method 2, when I have a linear equation in a trig function, I rewrite it. I subtract 1 and divide by 5, and I get cosine theta equals minus a fifth. And the first one, I'll just leave it alone. Sine theta equals 0. But now I have two equations, trig function equal a number. Right? So I solve each on the unit circle, method 1. Again, 4, 3, 2, 1 on this. I solve sine theta equals 0 on the unit circle, and I solve cosine theta equals minus a fifth on the unit circle separately. Now I can use x and y because my angle isn't x, so I don't need x hat and y hat. Sine theta is the y coordinate. Y coordinate equals 0 is this line of solution, right? There's the line y equals 0. And there's exactly two terminal rays. All right, I either go through here, which is theta equals 0, obviously, or I go this way, which is right a half turn, theta equals pi. So this one has two solutions, theta equals 0 or pi. All right. How about this one? Cosine theta equals minus a fifth. Oh, what's one solution to that? Cosine equals a number between plus and minus 1, always has one solution, what? I didn't get it across yet. We'll have to do another one. I'll wear you out doing these things. Inverse cosine, right? If cosine theta equals the number between minus 1 and 1, one solution is always inverse cosine. So inverse cosine of minus a fifth. Now, this is, for the cosine to be negative, it has to be in the fourth quadrant or in the third quadrant. Which one is inverse cosine? Again, this is the x coordinate. What am I saying? Second or third quadrants. This is the x coordinate, and so I get this line. X equals minus a fifth. I should draw it over here. I'll try and make it look more accurate. It doesn't have to be real accurate, just in the right quadrants, but we'll say x coordinate equal minus a fifth is this vertical line. I observe there's two terminal rays, this one, and that's it. This angle is arc cosine of negative a fifth, because the arc cosine is the angle between 0 and pi, right? First or second quadrant. And so now what's the other angle? I don't want this one, that's negative. I want this one. What is it? So here's one solution, arc cosine of minus a fifth, this one. Well, by symmetry, this one is also arc cosine of negative a fifth. So if I just took 2 pi back up this one, then I'd have it. That's what I get. This one is a whole rotation less this angle up here by symmetry. 2 pi minus arc cosine negative a fifth. There's the 4 exact answers. 2 of them easy and 2 of them hard, right? Now, what do the instructions say on here, just to follow them? I think we're just supposed to leave exact answers, so I'll leave it like that. Can I take away this minus? I actually can't. Cosine's an even function, its inverse is not. The inverse of any odd function is an odd function, but the inverse of an even function is not necessarily even. So you can't just take away these minuses. They generally are not. Inverse cosine is not an even function, only cosine is. But sine and arcsine are both odd functions. All right. There it is. Now we feel like we're experts, right? When you can do all these quickly, right? Then you're good. It's like Hogwarts, right? It's not good enough to see the spell. You got to practice until you can do it quickly when the dragon's attacking or something. So here's the last spell for the, if you like, for solving these trig equations. Quite a workout, huh? Well, I haven't left myself enough time to go into the next section, so maybe what I'll do is just see if there's any questions on this section. Any of these give you trouble, or we could do a simpler one that would help out? This is what I want you to be able to do in a week, is stuff like this. I know this will be a harder test, so I'll probably be a little gracious on points and scores. But seriously, if you go on for science classes and that kind of thing, you get these kind of problems in there, and you want to be able to solve them. I don't want to start the new section for lack of time. Let me do this one then. Oh God, I'm way over. I'm sorry. Yeah, I went way too long. My apologies. So tell me when I do that again. I have so many different hours. They end at different. Time to get out of here. Take some questions next time.